Alright, so this video is going to be about tanks. We have two tanks here. We have the blue tank right here, that's Team Blue, and down here we have a red tank, which is Team Red. And in this scenario, they're enemies. We have the blue tank is got the high ground and the red tank's got the low ground. Let's kind of take a look at what they're gonna do. Okay, so we see that the blue tank is starting to make its way over to the edge, gonna to give it a better vantage point, a better shot at hitting the red tank. And then once it gets to the edge, the red tank is going to start traveling. As it's going to raise its tank barrel to compensate for the height difference. It's going to get right to the edge, and right before it has its barrel lined up, the blue tank, since it made it to the edge faster, it made it there first, it's going to fire out its projectile first. And we see that little orange dot is the projectile of the tank. And sure enough, right before the red tank is able to fire, the blue tank lands a hit, and it incapacitates the red tank's tank. The red team's tank, and incapacitates it. So what I want to look at in this scenario is the location, velocity, and acceleration of this projectile as it travels through the air over time and eventually hits the red tank. So first I want to look at the projectile's location in the y direction, which is its height. So I have some markers set up. I have that the distance, roughly the distance between the two tanks, is 13 units, and at a height of 6.76 units. So when I'm looking at its position in the y location, I'm only concerned with what its height is as time goes on. The way that I can describe this curve that the projectile took is I'll write S, Y, and S is commonly used to denote something's position, and the subscript Y means that I'm only looking at the projectile's position on the y-axis, which is the height here, and that's the y-axis. So the way commonly that you write an equation of this kind, we would say it's a times t squared plus b. So there's two constants that we don't know what they are, and two variables, one independent variable, which it's only time, and the position on the y-axis varies based on time and the values of these constants. Okay, along with its position in space as height, we want to look at the velocity in the y direction. And the way that, if we just look at what the velocity is doing, at the beginning the velocity is 0. It's not traveling down, it's not traveling up. All it's literally at 0 at time equals 0. But as time goes on, you'll slowly get, your velocity will slowly start to increase in the negative direction, and finally, wherever it hits, it's going to be at its maximum velocity. And the velocity can be shown as 2 times a times t, because velocity is the derivative of position. And then finally, I want to look at the acceleration in the y direction, which just equals 2 times a. And that's because acceleration is the derivative of velocity. So I'm assuming that these tanks are on Earth. So what we can derive is the acceleration on Earth due to gravity is equal to negative 9.8 meters per second squared. And so now that we know acceleration is 2 times a, which equals negative 9.8, we can solve for this unknown constant a by just dividing both sides by 2. We see we have negative 4.9 is a. So we've actually found the first piece to the equation describing its position in the y direction. So we've solved for this not variable, we've solved for this constant a. Next thing we want to notice is that the projectile's initial velocity in the y direction is 0. The moment that the projectile leaves the barrel, it's not going down or going up. So at time equals 0, if I put 0 in place, the y location of the projectile is equal to 6.76. So this is 6.76 is equal to 0 times a. Well, that just negates that, and all you're left with is b. So if I clear that up a little bit, we have that a equals negative 4.9 and b is equal to that 6.76. Oops. So now we've found the two missing pieces for the equation describing the projectile's location as time goes on. So what we see is that the position in the y-axis is negative 4.9 t squared plus 6.76. So what we can do now that we have this information. So now that we have this equation, what can we determine about the projectile's location? Well, if we set the y value to 0, then what we're really asking is at what time does the projectile land, or basically have 0 height? Meaning if it starts here and it ends, here, what was the time that it took to get to that point? So let's go ahead and do that. I'll give myself some room. So if we set 0 equal to negative 4.9 t squared plus 6.76, and if we wanted to solve for the unknown, then we would just subtract 6.76 from both sides, and we'd have negative 4.9 t squared. So now we would divide both sides by negative 4.9, and we get roughly 1.38 is equal to t squared, and then we just take the square root of that, and we get that t roughly equals 1.17. It could be plus or minus. Mathematically speaking, it could be plus or minus, but if we took the negative, then what we're actually looking at is someplace back here, some point right here is the negative 1.17. But since we know, it was impossible for the projectile came from the tank, it didn't come from the ground, it didn't just spawn some energy and shoot itself up. So we know that the negative value is an erroneous value. It's something that we don't have to worry about. So we just take the positive. So what this is saying is if this was all in seconds, right? Like if this is time 0, then this would be time 1.17 seconds. So it would take 1.17 seconds for the projectile to start from here and to travel all the way straight down and be at 0 height. So what we know is the time it takes to get to the projectile, and also we know the distance to the target. So what we can say is that I already forgot it. 13 units, we can say meters, but it really could be anything, is equal to 1.17 seconds. So that's something that we know now, that the projectile travels 13 meters in 1.17 seconds. And that's roughly 11.11 meters in a second. So that actually tells us what its horizontal velocity is, because if if it missed, right? Like if it came up short, it wouldn't have gotten to the 1 point. It wouldn't have taken 1.17 seconds. It would have taken a shorter amount of time because it wouldn't have made it the full distance. So if it starts at, and I know this is a little bit wrong, this is actually time 1 here. So from time 0 to time 1.17 seconds was 13 meters. So in order for the projectile to have made it to the target, it would have had to have been traveling at this speed or this velocity. So that actually leads us into our next part, is looking at the position in the x-axis, the velocity in the x-axis, and the acceleration in the x-axis. So the position in the x-axis, so we think about what's going on here. It exits the barrel with a certain amount of velocity in the x direction, the x-axis, the horizontal axis. Now there could be some wind blowing back. It could have some force, depending on the mass of the projectile. It could feel there could be an acceleration against it. There could be an acceleration that helps it, moves it, makes it actually travel further than it might want. In this example, we're just going to assume that there's no wind speed that's going to affect it in such a great amount that it has an effect on the values. Whatever the wind speed is, or the acceleration, that would have to be measured with some sort of instrumentation, and really it would just you would follow the same methods of finding the acceleration, similar to how I found the acceleration in the y direction. You could find the acceleration in the wind's acceleration in the x dimension. But yeah, I'm gonna assume that there is zero acceleration left or right. In this instance, we're kind of working backwards. At first, I had an equation for the y position, and we could go in that order as well. But what I want to do is start with the acceleration and work my way backwards. So knowing that acceleration is the derivative of velocity, I can take the antiderivative of acceleration to get velocity. So the integral, or the antiderivative of 0, is just some constant, and that constant is Vx. It's whatever the velocity was when it left the cannon, because and that makes sense. If there's nothing else acting on it, it'll go the same distance in the same amount of time, same distance in the same amount of time. Like nothing's accelerating it forward or backwards, so it's just a constant velocity. So that makes sense that that the velocity is a constant, and we figured out what that number is. it's 100. It's 11.11 meters per second. The equation for its position on the x-axis is the last part. And again, working backwards, we know that velocity is the derivative of position. So the antiderivative would just be 11.11 times time, whatever that time is. So at time 1, it's traveled 11.11 meters. At time 2, it'd be 22.22. Time 3, 33.33, so on and so forth. It only gets, it actually wouldn't get more greater than time, 1.17, because by then it'll have traveled 13 meters and it will have hit the ground, so it won't be able to travel any further in the x-axis. So yeah, just wanted to kind of clean this up a little bit, get the main equations down. We said that the position in the x direction, the equation is negative 4.9 t squared plus 6.76. Its velocity in the y direction is negative 9.8 t, and the acceleration in the y direction is just negative 9.8. And then we said the acceleration in the x direction was 0. The velocity in the x direction was just, I'm not sure what to call it, VO or VO in the x direction. Basically, it's equal to V. It equaled 11.11. And then the position in the x axis was 11.11 times time. Just one final thing, just to show what the graphs kind of look like of each. This would be the acceleration would just be, if this is 0, then this is negative 9.8. The velocity in the y direction, is going to have some kind of downward slope, and the rise over run is going to give you your negative 9.8. This point at t0, actually, so this isn't t0. This is t0. Actually is going to start right here, because what we saw was back up here, the velocity, at time 0, it's not up or down, but immediately after it starts going down. So right here is where the velocity starts going down. It's a downward slope the whole time, but all these values are positive values of y. So really time 0 starts at the point where it crossed. Now we can kind of transpose and do the same thing down here. So this point here corresponds to this point in time here. And then if we look at the y component, this might actually this might actually give a better idea of what's going on. Let's start like this. Okay, I want to start sorry, start this here, start that here. This is time 0, and so remember what we saw was that here's the point, here's the height at which it left the cannon. Everything back here didn't actually occur. This just represents the inflection point of the parabola, meaning that this point here is where the projectile was at its highest point. At no time before or after this point here did it ever go any higher. It's always lower, and really we're not thinking about what happened back here. We're only thinking about what happened, starting at time 0 when the projectile left. And I know I just destroyed my graphs, but hopefully that kind of gives an idea of what's going on.